to episode 6 of Dielectric Videos. So today I thought I'd go into a little bit of information on electrical theory and fundamentals. Now I'm not going to get very far into the math behind why all these electrical phenomena take place. I wanted to just do a very brief conceptual overview of some basic electrical fundamentals so that you can kind of better understand what's going on in the circuits that you build and the circuits that you design. So I'll start out, of course, with a voltage source such as a battery. Now, you don't really need to know what happens inside the battery. There's an electrochemical reaction that produces positive charge at the anode of the battery and a negative charge at the cathode of the battery, but that's not really important right now. But what you should understand about this voltage source is that it has a positively charged side and a negatively charged side. Now, what do I mean by positive and negative charge? Well, a positive charge in an electronic circuit means that it has a lack of electrons. And the reason for that is that an electron, which if you've taken a chemistry class you'll know is that tiny particle that you find in the shells surrounding the nucleus of an atom, is actually a negatively charged particle. It has this negative electrostatic charge about it. And when you get a bunch of electrons in one place, and then not very many electrons in the other place, there's going to be a potential across these two parts of the circuit. Now, a potential in the international system of units, the metric system of units, is measured in the volt. A volt is essentially how much force, or how much electromotive force the electrons will produce in an attempt to get somewhere else where there aren't a lot of electrons. And that's really an oversimplification of what potential really is, but essentially you can think of potential as the sort of driving force to get these electrons at the cathode to move up into the anode through whatever your circuit is. Now that potential is exactly what allows electrical circuits to do work. So if I run a wire from the negative side of this battery to, say, let's just say we have a light bulb here, and then I run the other side over to the positive side of the battery. Well, these electrons down here are going to want to flow through the light bulb and flow back to the positive side of the battery, and by doing that, they are going to do work on the light bulb. And work is essentially the exchange of energy. You're turning electrical energy into thermal and light energy in the light bulb. Now, before I talk about how the work is actually getting done, I should mention that besides voltage, which is the potential in a circuit, we should also discuss current. Current is basically the counterpart to voltage, which is more of the quantity of the electrons moving. If voltage would be the pressure in a hydraulic or a pneumatic analogy, then current would be the rate of flow of that material, the rate of flow of electrons. Now, current is measured in amperes, or more commonly shortened to just amps. Now, an amp is what's called a coulomb, and hopefully I spelled that correctly, per second. It's a unit of flow rate. Now, an amp means that 1 coulomb of charge is flowing through the circuit every second. And a coulomb of charge is the amount of charge carried by a huge number of electrons. Now, I'm talking about just a massive number of electrons. To be exact, it is, to be approximate, it is about 6.24 times 10 to the 18 electrons. That is a big number of electrons. That means that a lot of electrons are going through the circuit every second to create a current flow of 1 amp. Now, when you have current flowing through a circuit at 1 amp, it's important to note that per Kirchhoff's current law, it's going to be flowing at 1 amp through the entire circuit. No one part of this circuit is going to have extra current flowing through it than the other. Now, in future videos, I'll talk about buck and boost converters, as well as transformers, which have methods for changing the amount of current flowing through a circuit. But in those cases, you're essentially setting up two different circuits. in the case of a simple circuit like this, the same amount of current flows through the entire circuit because in order to make these electrons flow, they have to have a place to go. They can't just pool up in the light bulb. They have to actually return back to the battery on the other side. So now that I've introduced the concept of current and the concept of voltage, I should look into the relationship between the two. And the relationship between current and voltage is actually denoted by a value known as resistance. And resistance is essentially the limitation of the amount of current that can flow through a circuit at a given time. Now, if I got rid of this light bulb in this circuit and I just connected these wires together like this, assuming this was an ideal battery and assuming these were ideal conductors, an infinite amount of current would flow through this circuit. It would just go so incredibly fast that it would just, all the energy in the battery that was stored in this would immediately be depleted. So, to make this an actually useful circuit, we have to actually introduce a resistive element. Now, the symbol for a resistor is this squiggly line. And basically, this is an impedance, or, well, an impedance would be if it's alternating current. I'll get into that later. But this is a resistance against the flow of current through the circuit. And what I mean by that is if you had a certain amount of voltage, say you had across this resistor, you had 1 volt. Volt, if I spell it correctly. So we would assume this is connected to some sort of power source, whether it be a battery or a power supply, and we'll just say positive, negative, like that. So if a volt is being placed across this resistor, well, how do we know how much current is going to flow? Well, that relationship is determined by Ohm's law, and I'm actually going to see if I can fit that into the last part of this paper here, but Ohm's law states that the voltage across a resistor like this is equal to the product of the current, I being the current, and I'll just write that out, multiplied by the resistance across that circuit. Now the resistance is measured in ohms, and ohms have the symbol, the omega symbol, to represent ohms. Now because the voltage is the current multiplied by the resistance, and let's assume we have this 1 volt power source driving this resistor circuit, well, that means that we have 1 volt equal to the current times the resistance. Now, just to make this relatively simple, I'm going to say that this is a 2 ohm resistor, arbitrarily. So that means we can substitute in a 2 for this R. And if we solve for I, we should get that I is equal to the voltage divided by the resistance, which would be 1 volt over 2 ohms, if I draw the omega very well. And therefore, the current in this circuit would be 0.5 amps. Half an amp will flow through this circuit continuously because of this resistor. Now, going back to the topic of work, work is essentially the change in energy, and work is actually a measurement of the exchange of energy from one medium to the other. More specifically, I should start out by talking about power, which is the amount of work that's done in a certain amount of time. Now, in electrical theory, power, which would be, you could write it as P, is equal to the voltage across an element of the circuit multiplied by the current flowing through that circuit. And if we substitute in our values from V equals I times R, we can actually solve this for basically any 2 variables that we want and for power. So to use the example that we just had, we have calculated that the voltage, well, we know the voltage across the circuit is 1 volt, and we calculated that the current across the circuit is half an amp. So the power would be 1 volt times 0.5 amps, or 0.5, well, what do we measure power in? What is your coffee maker or your space heater rated in? Well, it's rated in the watt. And the watt is a unit of power. That is a unit of work per time. A watt happens to actually be 1 unit of work, so 1 joule per 1 second, which would be equal to the equivalent of a volt times an amp. So well, I can just write that as V times I. Or, so I'll move on to the next page, and we can actually discuss a bit more about the relationship between power, work, and Ohm's law. All right, so let's say we want to apply the concept of power to a more practical circuit. Well, let's say that we have a resistance circuit set up where you have we'll say you have a 10 ohm resistor, and you have that wired up to a power source that delivers, let's say, 10 volts. Well, we want to figure out how much heat this resistor is going to make, and that way we can figure out how much power we're going to dissipate over and how much work we're going to do over time. So we have that this resistor is 10 ohms and 10 volts. So 10 volts equals 10 ohms times the current. And when we multiply this across, we will once again get that the current is 1 amp. Substitute that into the power formula, and we get that power is 1 amp times this 10 volts across the circuit, which is 10 watts. Now, if you were to use just a regular, tiny half-watt resistor that you might find in an electronics kit, and it was actually 10 ohms, it would basically burn out almost instantly. So it's important to note that you must have a place for this thermal energy to go, otherwise components are going to break. That's where, of course, power calculation is an important thing to do in an electrical circuit. But now that you probably understand the basics of power, voltage, resistance, the relationship between them, I'll move on to a slightly more advanced part of a circuit, which is the capacitor. Now let me just start a new page so I can get into the capacitor theory. Alright, so we want to talk about capacitance. Now, in a circuit, it's often a good idea to be able to store some energy in something other than the battery. So if we have the battery to start, or whatever power source you use, this could be a benchtop power supply or really anything, well, we might want to be able to store a certain amount of power. So I'm going to hook up a switch. By the way, this is the symbol for a switch in an electronic schematic. And this switch is going to go over to a capacitor, which are essentially two parallel bars. Sometimes one is curved to denote whether it's polarized or not. And this capacitor is then going to be connected to the negative here. Now, when we initially close this switch, a bunch of current is going to flow super fast into this capacitor, and it's going to charge the capacitor up. Now, one thing I didn't mention in the previous part of this video, notice I'm drawing the flow of current from the positive over towards the negative. Current, in terms of conventional current, does flow from positive to negative. However, electrons, which is the flow of charge and of electrons, flow from the negative side over to the positive side. But when you're talking about a circuit and conventional current, generally it's denoted with the current flowing from the positive to the negative side. So the current's going to flow from the positive side of the battery into this capacitor, and this side of the capacitor is going to get to be very positive. Now, assuming the capacitor was neutrally charged initially and it didn't have a charge, by putting this positive charge on this side, you're essentially shoving out negative charge on the other side. Well, technically you're shoving out positive charge on the other side in response, which is going to satisfy the Kirchhoff's current law that all current through the circuit must be the same at all points. However, while you're doing this, if we zoom in on this capacitor, essentially what you're doing is you are making one side of the capacitor really positive, and in response you're making the other side really negative because you pushed a bunch of positive charge, or you pushed a bunch of charge carriers back out and back to the negative. So now this capacitor has a positive charge and a negative charge. Now, if I open up the switch here and it's no longer connected, this capacitor is going to retain its charge. And if I were actually to test this across with a multimeter, the multimeter would show that it was charged to whatever voltage the battery was. Say, for example, this was a 1.5 volt battery. That would be the voltage you get out of like a AA or any alkaline or carbon zinc battery. Well, this capacitor, assuming there's no leakage current through it, is going to say 1.5 volts, even after the battery's been disconnected. And if you were to then connect a resistor of some value across it, this would gradually discharge the capacitor, and in exchange, it would produce heat and do work, as we saw, until the capacitor finally discharges so much that it no longer has any significant polarity of voltage. It's back to its original state. So now that we have the actual practical conceptual look at capacitors in mind, we can actually look at a little bit of math behind this. The capacitance equation is C equals Q over V. Now, the V, of course, is the voltage across the capacitor, which in this example we identified as being 1.5 volts. The C is the capacitance rating of the capacitor, which will be measured in farads, or more commonly in microfarads. So the capacitance of this capacitor is going to represent essentially how much voltage it takes to fill the capacitor up with a certain amount of charge. Increasing the voltage will also subsequently increase the charge in the capacitor. If we do a little bit of quick math here, we can get that CV equals Q, or the capacitance times the voltage equals the charge. Now, I didn't already mention, but Q, it represents the charge of the capacitor, and Q, as we recall from the first part, is measured in coulombs as well, the amount of charge in the circuit. So the charge in the capacitor, essentially, since it's equivalent to the capacitance times the voltage, would then be dependent on the voltage, assuming the capacitance is constant. I'll do the example with the 1.5 volt battery. Let's say we have 1.5 volts times, and I'm going to use an example of a very, very large capacitor. Like I said, normally they're measured in microfarads, but to make the math a little easier, let's just say that this is 1 farad. They do make 1 farad capacitors. They're called ultracapacitors, but generally in your usual circuits that you'll be seeing capacitors in the microfarads or even in the nanofarads or picofarads, which are even smaller. But for the purpose of explanation, I'll say this is a 1 farad capacitor, and it's just been charged by this battery to 1.5 volts. Well, we can then calculate that Q is going to be 1.5 coulombs, or a charge of roughly 1.5 multiplied by the 6.24 times 10 to the 18 electrons. That's how many electrons we've pushed into this capacitor at 1.5 volts. So the relationship, as you can see, is that increasing the voltage increases the charge in the capacitor, and thus increases the power with the square of the voltage. And if you actually do the math behind this, you're going to get that the power stored in a capacitor does increase linearly with the voltage. It's a little bit more complicated math that I'll get into in a future video. So, with that being said, the last thing I want to discuss, I could get into other components, but really those are the most essential and basic parts of the circuit. I'll briefly touch on a couple of other components. You have the inductor, which essentially looks like this. The inductor is basically a way to store not electrostatic charge like in a capacitor, but it's a way to store a magnetic field. So if you allow an electric current to flow through an inductor, it's going to build up a magnetic field above it and around it. You'll usually see them actually built as little coils of wire around a little ferrite core with 2 legs. And what will essentially happen is if you turn the power off here, the current or the field in this inductor will collapse and generate a big surge of voltage in the original direction of the field. And that, of course, is useful for making things like boost converters that can increase the voltage at the expense of more current. Now, I'm not going to go into the math behind inductors. I just wanted to touch on that briefly because this is just an introduction video. I'll also talk about transistors. So transistors are essentially, there's many types. There's metal oxide semiconductor field effect transistors, bipolar junction transistors, all kinds of transistors. But essentially what a transistor is essentially a switch. And the way a transistor works is you have basically some of them, if it's a bipolar junction transistor, we'll call this the base. Some of them, if it's a MOSFET, which is a metal oxide semiconductor field effect transistor, we'll call this the gate. But basically the way a transistor works is you do something here, whether it's with voltage or current, and it turns the rest of the flow of current through this on or off, depending on what type of transistor it is. And transistors are essentially a sort of combination of a switch and a rheostat in one that allow you to use an electrical signal to change the flow of current through the device. Now, I just mentioned the rheostat, or also similarly referred to as the potentiometer. And a potentiometer is essentially, I'll show you the symbol for that, it's a resistor that can be changed. And you'll see this often as a dial that you can turn, or a little, they call a trimmer, where you put a screwdriver in to rotate the control for it. But essentially, you can adjust the resistance of the resistor, and usually this arrow will have an actual center tap on the resistor, so you can move it higher or lower with respect to one side of the resistor and the other side. But those are basically the components you're going to run into. Anything more complicated than this, I'll cover. My apologies for the skip in video just now. My camera actually ran out of memory in the previous, at the end of the previous segment of video. So I just got done talking about the basic fundamentals of electrical theory and some of the more basic overviews of components that you might encounter in electronics. Now, the last thing I wanted to mention in this very brief overview of electronic theory is the difference between direct current, or DC, and alternating current, or AC. Now, direct current is essentially what you would get out of a battery. If you have a positive and a negative terminal, the direct current is going to flow, conventionally speaking, in one direction forever. It's not going to ever change direction. It will just flow at that, whatever voltage the battery is, through the circuit, assuming there's something in the circuit, and back down to the negative, and it'll just do that until the battery is depleted. Now, the symbol for direct current is a dashed line with a bar above it, essentially denoting that there is a continuous flow of current relative to the zero position, and it's just going to flow like that basically forever. On the other hand, you have alternating current. This is what you would get out of your wall outlet, and essentially what alternating current does is it changes polarity frequently. So alternating current is denoted by the symbol like this. It looks like a piece of a sine wave. And on a graph of voltage versus time, an alternating current signal would look like this, as you can probably infer from the sine wave symbol. Now, what's basically happening is the signal between, say, the hot, or rather the hot over here, and the neutral is changing its polarity frequently. The reason alternating current circuits aren't referred to as the positive and the negative, which is not how you refer to it, is because there is no positive or negative terminal. The positive and negative roles reverse in alternating current. And basically what happens is, say the potential between this part of the plug and this part of the plug at one point might be very much positive, but a little bit later, 1/60th of a second, or rather 1/120th of a second later, it would be down here in the other polarity. So the idea behind this seems kind of pointless. It's like, well, why would you want it to change back and forth? It's actually quite useful because transformers allow you to switch alternating current to a higher voltage or a lower voltage and also change the current proportionately. You can check out episode 1 to see more about transformer theory. But this is the basic difference between alternating current and direct current. Alternating current changes its voltage relative to the 0 volt time axis here, and it increases and decreases at a constant rate. Now, a sine wave is not the only type of alternating current you have. There's also square waves and stair-step modified sine waves and all kinds of waveforms with sawtooths and pretty much anything you can think of that makes this same form of shape. But I'll cover those more specifically in a future video, perhaps when I'm talking about power inverters. So hopefully you now know the difference between direct current and alternating current, and I would hope that you can now understand the principles of electronics and how electronics work a bit better after watching this video. Now, as always, I encourage you to go out and try experiments on a breadboard, try some capacitor circuits, some resistor circuits, and get a multimeter out and take some measurements to see what voltage is being applied and what voltage changes as you modify the components. So thank you for watching this video, and I look forward to making the next one.